Welcome. In this video lecture, we will investigate pressure-temperature diagrams and what they can teach us about the conditions inside of the Earth that are capable of taking a solid rock and melting it to create magma.
This is the pressure-temperature, or PT, diagram. It will help us figure out under what pressure and temperature conditions solid rock begins to melt. That is, the conditions that generate magma. Let's start by considering the x-axis, temperature. Low temperatures on the left represent surface temperatures. As we move farther and farther right, temperature increases significantly. The y-axis is depth, or pressure. The top of the graph represents pressures at the surface of the Earth. And as we go farther and farther down inside of the Earth, pressure increases. We are able to explore PT space by examining where different scenarios fall within the diagram. This can help us to learn how and where rocks experience melting inside of the Earth. This bold line here is labeled the Peridotite Solidus line. This line represents the pressure-temperature conditions at which rocks in the mantle begin to melt. Peridotite is the name of mantle rock, just like basalt is the name of the rock that makes up the oceanic crust, and granite is the name of the rock that makes up the continental crust. Remember how in an earlier video we discussed the fact that real magmas are actually mixtures of solids, liquids, and gas? Well, this line represents the moment that melting first begins of at least some of the crystals that make up a rock. It represents the transformation from a complete solid, again, made up of minerals, to a mixture of solids and melts. The line itself could be either the beginning of melting, if you're moving this way, or the final step in crystallization, if you're moving that way. The other line over here, the dashed line, is the peridotite liquidus line. This represents conditions at which every single crystal in the sample would have melted. So on one side of the line, material is 100% liquid, and on the other side, it still contains some small proportion of melt. So just to reiterate, if we start with solid rock, it begins to melt as soon as the pressure-temperature conditions are the same as this solidus line. And then melting continues as pressure-temperature conditions change until you reach 100% melt if you cross the conditions that are described by the liquidus line. Conversely, if we start with a melt, we could investigate cooling. When pressure-temperature conditions match those described by the liquidus, then crystallization begins, and crystallization will continue until the solidus line is reached, at which point all of the melt in the sample will have turned into crystals and our sample will be completely solid. At this point, it would be an igneous rock. So if the solidus represents conditions when melting begins and the liquidus represents conditions when melting is complete, all of this area in between these two curves represents a magma composed of both melt and solid. Now, in the real world, these conditions over here of 100% liquid magma, well, they don't actually exist. So a lot of times when looking at these types of diagrams, you're going to see the solidus line, but no liquidus line. In that case, just like in this case, you will have magma on one side, so magma over here, and solid rock on the other. These final two curves on the left represent the Oceanic and Continental geothermal gradient. Geo meaning earth, thermal meaning temperature, gradient meaning change. So geothermal gradient is simply the temperature change that's experienced as you consider rocks deeper and deeper inside of the earth. So while this plot taken as a whole gives us a huge range of scenarios, some of which we might be able to recreate in a lab, it's only these two lines that are telling us the actual temperatures and pressures of the actual oceanic and continental lithosphere in the real world, beginning up at the surface and then showing us how those temperature pressure conditions change as we move down inside of the earth. What you'll notice if you examine these curves, the real geothermal gradients, is that they do not represent conditions of melting. This line represents pressure temperature conditions that would result in melting inside of the earth. And neither of these two lines manages to make it to the melt side of that Solidus curve. The fact that both geotherms are to the left in the real world, this means that the material underneath continents as well as the material underlying the oceans is a solid. It turns out that melting is actually incredibly rare inside of the earth. This is why the lithosphere and the mantle are both solids, a fact that you should remember from studying the mechanical layers of the earth. However, volcanism does exist, so we know that it is possible to melt rock naturally. So how does melting happen? Where does melting happen? Well, more on that next time. For now, since we understand how to interpret pressure-temperature diagrams, this video lecture is complete. See you next time.